It is Doug McIntyre again, and I'm bringing to you a little primer on reading and thus formatting future one-line diagrams. This is where, as a plans examiner and as an engineer, I found that a lot of time will be spent. And so I wanted to go over this for people, when I'm reviewing a set of plans, no matter really how large, this is where I kind of start because this is where a lot of errors are made. But this is also an opportunity to um, speak to the electrical system probably more thoroughly than anywhere else, at least from the power perspective. There's a lot of points here. So what I'm going to do is just move through them. And of course, you see my nice little disclaimer here. So we're going to move on from here. Let me show you the simplest form of a one-line diagram that I've ever created is kind of this. And what you'll see here then is a very, very basic one-line diagram. Um, this one is designed to just get the main points across. This is more of a residential, um, residential type one-line diagram. But you'll see our panel. That's our main panel board where all our circuit breakers are going to be located. You'll see that I have a note there for main circuit breaker. If there's not a disconnect, disconnects are required by code on the outside of a building, or really what the code's attempting to do is this piece of conductor that you see here is always got to be protected inside a building or home. That's where there's issue for fire. If this is the meter, and then that meter oftentimes will just set back to back with the main panel and with the main circuit breaker, that gets that accomplished. If that panel is meant to be more interior to the site, then you have the issue of needing to protect that conductor, like I said before. So we would put a main disconnect on the outside, usually with fuses. Those are relatively inexpensive and a good way to get that accomplished. So let me just run through some of the parts and pieces here. In this one, I don't really have everything that's needed, but I'll go into that in a second. You'll see it when I go over it. But this one is more shown. This is showing the grounding system, which is one of the opportunities for a one-line diagram. Many jurisdictions will just accept a ground per code type set of comments. This one is a little bit more detailed. It is really more designed to help a homeowner or an individual know how to ground within their home. So you'll see the concrete footer, or what we call the UFER, UFER, and infooting ground. And you'll see some description of how that works. 20 feet minimum concrete encased electrode with irreversible connections. You'll see the rebar that is up and capped. There's some exposure and whatnot. And then this is to the water system. This is true of any water system, is we make that connection within 5 feet between the valve and when the water pipe comes into the structure. That's going to be a component of any grounding system in a building that is fed with water, of course. And then there's this jumper across, and you'll see my note here, size per NEC table 250.66, and this is the grounding electrode conductor. And then this is also a grounding electrode conductor going up to pick up the UFER, and 250.66b tells us that that doesn't have to exceed number 4 copper. And then when driving ground rods, which I'm not showing here, the ground rods have a number 6 as the maximum required by code. But this is a really basic one-line diagram. Let me get to something that's a little bit more complicated. And this one is from a job that was accomplished kind of recently by our firm. It is commercial. It is for a restaurant, and so it has more detail in it. And so let me show you kind of the components here. Just going through this as quickly as possible. I don't want this to be as long a video as some of the others can be, but what you'll see, this is the utility transformer, and that's going to be provided by your local electric utility. This one is a larger service, 800 amps, and so you see you'll have a CT cabinet where the metering CTs or current transformers go to feed the meter. And then what you'll see here is you'll see some callouts. This piece here, that's a main distribution panel. You see the main distribution panel, square D I-line panel. And the square DI line panel, I happen to know if you get the 1200 amp bus, it will take 400 amp circuit breakers as branches, which is what we wanted in this particular instance. And so each of these is a panel board that's used for power distribution within this restaurant. And then we have a main disconnect, which is required. Actually, if you look in the code, a service is allowed to have 6 switches, 6 handles, which often is called the 6-handle rule. We could have foregone this 800 amp main and then just use these 6 as our distribution, but we wanted the ability to add loads in the future. And so this panel board actually has room for quite a few more breakers. And so that's what we've done, is we've put a main on this so that we wouldn't be hindered later on. Now you'll see here are all the different feeder configurations. So you'll see you'll have 2 sets of 4 3/0 and 1 number 3 ground in a 2.5-inch conduit. And that's being called out. You'll see the circles. They've been added here. So we've got the 2 situations here where these multiple sets of 3/0 are going on. Now we have I'm just noticing a little error in my main circuit breaker here. This should be a 400. Oops. So I'll fix that now and be done with that. Extra points if you caught that. But then you'll see here these different callouts here: 4 4/0, 1 number 4, 2.5-inch conduit. And so these are called out for the 225 panels here. And then we have a 100 amp panel here, panel LP, and it's fed with a 100 amp circuit breaker, and it has 4 number 2s with 1 number 8 ground and 1.5-inch conduit. And so when these are being reviewed and when these are being designed, we design these feeders to meet at a minimum the ampacity of the circuit breaker that's feeding them. Sometimes we'll enlarge these wires in order to accommodate, say, voltage drop or nonlinear loads, things along those lines. In this particular case, these are sized for the actual load that's going into these panels. And then you'll see panels that have subpanels. You see there's 2 subpanels being fed by other panels here. So here's a subpanel, K2, which is a 225, and he's being fed with 4 4/0. And so similar configuration to what you see down here. So that's panel K1, K2. Those are kitchen panels. And there's K3, which is a 225 fed directly from the MDP. And then K4, which is fed directly from the MDP. And you see it's fed with a slightly smaller circuit breaker. But we went ahead and ran the larger conductor to it because we have this particular lighting subpanel. And then we also know that they want to add more loads in the future to panel K4. Also, one of the things that you'll see here, you see this SCCA, that's short circuit current available, of 9,650 amps. Now, in some one lines, that's what you'll see is you have to, for most building departments, and certainly for your engineering study, you have to put that information. You have to know what these breakers and these panels are designed to withstand. Circuit breakers are rated at different levels in the tens of thousands, so 10 to 22 to 35 to 45 to 65, 100, etc. Different short circuit current ratings or bracings, as some people know them. Also, in this particular drawing, let me show you a fault current study that has been accomplished by this particular designer, and you'll see you'll see the different sets of energy. So you have different short circuit currents at the MDP, at K1, at K2, at K3, at panel A, LP, and then A4. And you'll see in these boxes the different short circuit current or fault current ratings. Or fault current available, I'm sorry. And so these different fault current available, that's important information. And the engineer can look at this. If he's reviewing it for his designer, he can look at this and he can see the length of the feeder, the type of the conductor used, the number of conductors per phase, all that kind of thing. And so you can kind of look at your general assumptions. Then there's these factors and multipliers that are just part of the program that this individual used, that we used to get this accomplished. And So what's going to happen is the designer or the engineer look at these numbers, and then when we provide panel schedules, we're going to schedule panels that are designed to handle those loads, or those fault loads, I should say. And so those are worst case scenario. We call that a bolted three-phase fault, which is if what were to happen, let's say we were to go into our bus and this panel board, for instance, or let's say this panel board, and we were to, turn the power off, run a bolt through all three of the phases, and then flip the main back on, it would have theoretically an available 9,650 amps of current available to it. And so we have to protect for that. And so these are the basic components that we're looking for in a one-line diagram. Now I have another one-line diagram here. Let me show you that one. It was prepared a little differently. And so this one is actually a 480 volt panel board. You'll see a lot of the same components. Sorry for the jumping around. See, here's the utility transformer. Here are, and what you'll see is tags. So this 4S1200, you'll see the 1200 amp main, the main distribution panel. It's also rated at 1200. We have a 1200 amp bus. This is going to give the contractor the ability to buy the correct piece here. And so, that's what we're trying to accomplish there. This one's 1200 amps at 480 volts, and so code requires that to be GFCI protected. We also have TVSS on this one. Now, just to show you a difference, you'll see these 3F90, 4F225, 4F225, 4S1200. Well, this has been a little bit different, and what we've done here is we've provided a feeder schedule. A lot of engineering firms will do this because it is a little easier way to communicate what it is you want, and then you can kind of figure out ahead of time exactly what it is you're going to use, and you just come through and pick out the key to the one that you need. And in this particular case, this is a generated schedule from Excel, and so this could be expanded and contracted to contain more feeder types, so that if you have panels of varying degrees, you have 3F, so these are going to be single phase 4 wires, so 3F 125, 3F 150s, and so 125, 150 amp. But then we move up to these 4F, so these are 3-phase 4-wire, and so you've got 4F 225, 250, 400, 600, 1200. What I try to do is rather than just putting this big long schedule on every plan, I want to put this one on there to encapsulate the ones that I'm actually using. I've got to be a little careful because I may leave one off. Maybe I have a 3F 175 or a 4F 175 that I needed on the schedule, but then I forget to add it to my feeder schedule. Well, then there's a little bit of a problem. Somebody has to issue an RFI to get that accomplished. A lot of times it gets caught in plan review, and somebody will come in and say, hey, look, you're missing a feeder for that. We want to know what that is, and that's a good use. Now you'll also see on this particular one, see SCCA less than 10 KA. So in this particular instance, this is an existing one line, and what's happening is a panel is being added for a tenant improvement to this existing panel. And so, it's 10,000 amps is the lowest fault current rating for any circuit breaker out there of normal commercial use. And so once it's less than 10, usually it's not necessary to put that information on anymore. In this particular case, I'm not sure if they got left on here because this was a remodel, but what you would typically see in this type of one line without that short circuit current study being set on there and scheduled, sometimes a fault current schedule, just like the feeder schedule. And then what'll happen is you'll see that SCCA equals, or equal to or less than or approximately, throughout. And so we would look for that, and that's something that's required before any panel board, on here. And then this is another thing that's required is a service load summary. Sometimes there's a schedule just for the MDP. Sometimes, like in this particular case, there's just this service load summary which we've created from our panel schedules that jumps in here and tells us that on this particular 1200 amp piece of gear there's 757 amps. And so that's how that's being kept track of, is this service load summary. If there's not a schedule for the main distribution MDP itself, then this is where that'll come into play. And so we'll look at this and we'll make sure that the factors are correct. The lighting is considered continuous, and there's 125, 1.25 factor, so 25% added for lighting. There's other miscellaneous continuous loads, which are, anything that stays on for 3 hours or more is considered continuous. So you might have other loads that are considered continuous. Different heaters are required by code to be considered continuous, and so we get that. And we have miscellaneous non-continuous loads. So you see a lot of 1.0s. Kitchen equipment. In our particular case, we didn't have a demand factor that was required, but in a kitchen, like a big commercial kitchen, you can take different factors, and sometimes as low as 0.55 or 0.65, because they know in a big commercial kitchen that there's diversity. They can help us have a more right-sized or realistically sized electrical service. So you see, just a couple of different one lines. There's 3 different one lines. In this particular one, just looking at the overarching view, excuse me. You see your main distribution panel. You've got your other distribution panels, the high voltage, and then you've got this larger distribution panel over here that's 400 amps, and it's carrying a larger chunk of load out to elsewhere in the building in order to just distribute your power. And this particular building was about a 30,000 square foot building, and so we like to get the power out where it's utilized, keeping branch circuits as short as possible. Now let me just show you a couple of panel schedules, just to familiarize you a little bit with the kind of the harmony there. So this is L1A1. This happens to be this panel here, and it's a single compartment panel, and you'll see L1A1, it's got all sorts of things. See this 10kA short circuit series rating. It's a 208 volt 120 volt 3-phase 4-wire panel, and you can see all the loads as they're summarized here. And this being that short circuit current series rating, now to 10K, actually those are fully rated breakers. Series ratings allows manufacturers to test their 10K breakers, for instance. They're cheaper breakers with the more expensive breakers, and they put them in series together, and then they can achieve a higher rating that's necessary to accommodate the available fault current. And so you'll either see fully rated or series rated there, and it would have been good for us to have had fully rating on there, but like here's a 35K short circuit series rating. This is a 480 volt panel. Well, 480 volt panels, the minimum short circuit rating that you'll find is 14 for individual branch circuit breakers. And so what we're saying is that if these breakers that you go by, these 20 amp 3 poles that you see here, these 20 amp single poles, if you put those in series with another breaker and the manufacturer has tested them to work at 35K with the cheaper breakers and maybe one larger expensive breaker in the MDP, then there's a cost savings to be accommodated there. Now there is an exception within the code that keeps you from doing series ratings, and but we won't go into that here. So that's just a quick overview of one-line diagrams, reading them and using them. So hopefully this was informative, helpful, enjoyable, whatever. If you have any questions, just post them on the feed. Thanks again. Doug McIntyre, PE, signing out.